Okay, so I'm wrapping up a little bit of material from the previous PowerPoint, and then we'll move forward to the PowerPoint that I posted with the date under today. So what we've been looking at is the generation of muscle contraction and how it happens. And we are talking a lot about adenosine triphosphate and how that works and how it's regulated. So we had these different physiological processes like the direct phosphorylation, which gave us a little bit of contraction in a quick way. We had something called anaerobic respiration, which also gave us a little bit more energy for contraction, also happening in a fast way without the presence or use of oxygen. And then we had the aerobic respiration, which was a longer metabolic pathway. So it had a slower energy production, but it was giving us a lot more ATP, therefore a lot more energy contraction ability, right, for a longer and sustained period of time. So we talked about that, or I talked about it previously, and these three slides simply break it up again. They're repeat slides, okay? So so what happens during sports activity? Um, we have our aerobic endurance activities, right? And we can right away think, okay, so that's the aerobic pathway, right? It requires more energy. So because the length of time that the muscle needs to undergo its work is so long, it is going to rev into these aerobic pathways and it's going to utilize them. There's something called the anaerobic threshold, which is a point which the muscle converts to an anaerobic pathway. So let's say I go out, I haven't run for 1 year, maybe two, maybe three. I haven't run for like 2 years. I'm trying to think the last time I went out for a jog. But anyway, so then I'm like, okay, I want to do 3 miles. So I start running and I'm going to hit, because I'm not conditioned the way I used to be, I'm probably going to hit my anaerobic threshold faster than if I had been running every week for the past year. So when I go out and I try to run 3 miles without having run in a couple of years, I convert to an anaerobic pathway sooner. Right? I'm not going to utilize I don't have as much endurance. I'm not going to be able to use this oxygen, um, this oxygen rich and aerobic pathway for as long as I did before. I'm going to hit it faster. And what that means is I'm going to fatigue faster, right? Because there's a limit to the amount of use that we can do with the anaerobic pathway. So this is what leads to fatigue. So it happens later in exercise for athletes versus non-athletes. And by the end of this hour, we should have a little bit more of an understanding about why or how this happens. So let's keep going and look at it. So there's two factors that are happening. We have ATP, energy reserve for muscle contraction, which is always there, and we have the ability to quickly generate it right through our anaerobic pathway. That's a quick generation of it. But we also have the endurance aerobic pathway that we can utilize. So there's two angles here. One is that if we're simply doing what's happening in this picture, where we're going from rest to a sprint to a run, right? We're going to use those the ATP reserves and the quick glycolytic pathway first. That is going to happen first. But then when we go into this prolonged duration exercise, we're going to rely heavily on our aerobic pathway as that continues. So this is kind of like where it goes on. As this woman keeps running and running and running, right? Eventually she's going to reach her anaerobic threshold, probably much later than I will, based on kind of how she looks right now. She looks really good. Like she can do this for like maybe she can go 15 miles, who knows. But the point is, if she keeps going, she's going to reach that threshold. Everybody will at some point will reach that threshold, and then they're going to start to use these pathways again to get more of the energy. So that's what I'm trying to make clear here, is that yes, we use these pathways to rev up and start, and they're accessed at first, Once we get into this prolonged duration exercise, we then continue until we reach another threshold in which we have to fall back on these shorter units of energy production again, right? And that's when we hit fatigue, because this won't last. We won't be able to keep generating and regenerating enough energy to keep going, right? Because we're only getting 1 or 2 units of ATP per metabolic pathway. All right, so I feel like that's the best way I've explained it yet. So I think you guys are going to get this. So, okay, so pause on that. We're going to talk more. So what's excess post-exercise oxygen consumption? Okay, so when you exercise that you breathe really heavily, the more exercise you do, and you might notice that after you're running for a while, you stop and you still breathe heavily, even though you're not running anymore, and then eventually that dies out. So so you do have an increased respiratory rate and a depth of respiration during exercise. However, that's not what this is. So what this is talking about oxygen consumption on a microscopic level. Okay, so I know that we have that gross effect of let's call it even like hyperventilating, but like of taking in a lot of oxygen. But what we're talking about here is something else. What we're talking about here is returning the muscle to the chemical formation, the metabolic level that it was at when it was at rest. So in order to get there, we have to start to rev down or replenish the places where things have shifted in the processes. So we need to get oxygen reserves, the normal amount of oxygen within the cell unit to have to go back to where it was. The lactic acid that we created, right, with that as a byproduct of the glycolytic process way needs to reconvert to pyruvic acid. The glycogen stores where we pulled from the glycogen, those need to get replaced. Everything has to go back to where it was, including the ATP and creatine phosphate, because when we are at rest, we start with a certain amount of chemical availability within the body that we're going to pull from. So we need to get back to that because we've used it. So for this, there needs to be more oxygen. And this is referred to as excess post-exercise oxygen consumption, and it's or oxygen debt. And it's the reason why we need to be utilizing more oxygen after we exercise to regenerate back to our original state. Okay, so this time frame when we have this excessive post-exercise oxygen consumption, when the body's pulling more units of oxygen is happening. So here we're at rest. During our exercise, we go into oxygen deficit. And then here we're in that place where we have our recovery time, and we're going to have the excess oxygen consumption. So that's this time frame. High oxygen ATP demands in the active muscle. These are the reasons why. And again, the buildup of the lactic acid in the liver and the muscle during the activity just needs to be regenerated. So all of these things are associated with the EPOC. Okay. So fatigue happens on multiple levels again. So let's just look at this. We have athletes and we have non-athletes. So we have athletes will have more mitochondria in their muscles due to the training that they've done. This will allow them to shift to the anaerobic respiration later in exercise. The non-athletes will have fewer mitochondria and will shift to the anaerobic respiration sooner, right? Therefore fatiguing sooner. So again, this is just laying it out again, how our physical fitness level is going to relate to our fatigue and why it happens at a microscopic level. All right, but I'm going to read this to you now, and then I'll show it to you again. So this is a little heady because I haven't introduced the slow twitch fibers yet. But as you get further along into a run, you're going to get tired because of these slow twitch fibers not working as efficiently. You start to recruit some other fibers to help maintain pace, but these fibers are going to require more of our reserve glycogen, and they're not as fatigue resistant. So it won't be long before you find yourself slowing down and stopping. Okay. So in addition to the pathways that we go through, there's also this concept of slow twitch, intermediate twitch, and fast twitch fibers, which we'll introduce next. So fatigue is the inability to contract despite continued stimulation. And here's the theories behind why. If we go back to when we were talking about the sodium and potassium moving in and out to change the composition of the membrane potential, if we talk about the amount of calcium that is going to flood in and out of a cell to then activate the contraction, right? If we go back to those lessons, right, then these are some theories of why we get fatigued, that we change these levels of chemicals, and it disrupts the ability for the muscle to contract at that level. There's also some theory that it might interfere again with the calcium release from the sarcoplasmic reticulum with this, it's called an inorganic phosphage from the creatine phosphate and ATP breakdown. So this is another theory of why we get muscle fatigue and we can't just continuously contract forever. Okay. The last two theories is that the decrease in the ATP synthesis and there's an increase in magnesium can interfere with the voltage sensitive T tubules. So again, if the T tubules aren't communicating the signals for contraction, then you're not going to get it. So this is the other theory. And then last one, the least theoretical and most tangible of them is a decreased reserve of glycogen. And again, even though we'd say most of our energy is coming from our aerobic pathway, the inability to generate based on the amount of glycogen store is also a reason why we would get muscle fatigue. So it's not that we don't have the energy, the ATP generation, but it's rather the fact that we have all these processes disrupted and needing to reset and in order to continue. So those are the theories based on it. Okay. So we're going to look at slow twitch and fast twitch muscles, fibers within skeletal muscle, and then we'll take a quick peek at smooth muscles here. And then hopefully after slow twitch and fast twitch, it'll come together a little bit more. So force of contraction in the skeletal muscle, right, is going to have to do with, we talked about summation of frequency. So the more neural firing you get, the bigger the wave is and the stronger the contraction force. Remember that this is a large number of the muscle fibers recruited, so many muscle fibers. Size, now we get size of the muscle fiber. And then there's this other thing where if my muscle is stretched and I want to contract it, if it's stretched past zero, so I have a little bit of hyperextension, I'm not going to generate as much force as I'm going to generate in a shorter contractile space. So when you stretch it past the resting length and then try to make a contraction, that actually decreases the amount of contractile force. Okay. But if it is, but when you're starting at zero, you have a long range of contractile force. So velocity and then duration. What determines the velocity, what determines the duration. So this is where we get slow, fast muscle fiber types. The load, that would be if I can contract, my velocity is faster, the smaller the load. And then the recruitment, which goes back to the size principle, right? The smaller units are recruited before the larger units. And So that will also determine the speed of contraction. So what we're looking at specifically today is muscle fiber type. So we have slower, fast fibers. And it's the speed at which the myosin enzyme, ATPase, right, splits the ATP. So, so it's about how fast that processing happens. And that's the pattern of electrical activity of the motor unit, of the motor neuron. That can also be affecting the speed of the contraction. So the pattern of electrical activity again would be like deep, deep, deep neural summation. Neural firing, 1, 2, 3 versus 1, 2, 3. Metabolic pathways used for ATP synthesis. We have the oxidative fibers, the glycolytic fibers. Let me go back. So we're going to have like these slow oxidative fibers using the aerobic pathway, and we're going to have the glycolytic fibers using an anaerobic pathway. This makes sense based on what we know about muscle contraction anyway. We're starting to get a little more specific with a little bit more specific naming. So what are slow oxidative fibers? They're also known as red slow twitch muscles, slow twitch muscle fibers. So they use oxygen, all right, and the fact that they're red, like myoglobin that is carrying oxygen in the blood, right? Slow twitch, all these kind of associations can get you to that place where you're thinking aerobasis or use of oxygen. These are weaker contractions. They're also slower. The split from the ATP is slow to meet the muscle demand. It gets a slow but a long contraction with not a lot of fatigue, and that's important. Again, they can use the oxygen pathway without depleting oxygen fully. And also, the primary energy supply is the fatty acid, right? It does not fatigue easily, and it's recruited first. So we have the order of recruitment size principle, and now we're talking about recruitment with muscle fiber type, right? So, so slow oxidative fibers are recruited first. Weak contractions, but they can stay a long period of time. So, for example, when you're sitting in an upright position, your muscles are contracted to maintain upright position. This is a little different than tone, all right? This is because if I'm kind of hunched over, there's not, maybe I'm like, now I guess you could say like my neck muscle is really taking the most force of contraction. So if I want to like transmit that force into my back, I'm going to get a weak but constant contraction in the postural muscles. So slow oxidative, fast oxidative, and fast glycolytic. So we looked at slow oxidative. All the fibers in one motor unit are the same type. So these exist within each skeletal muscle. You're going to have all these types, but within each motor unit, you only have one. And recall that a motor unit is that nerve that stimulates that one muscle fiber. Or one group of muscle fibers. The genetics is going to play a determination in how many of these fiber types you have per gross muscle area. This is why some people are like naturally or genetically better at certain sports than other ones, but we can develop and exercise any one of these types to fine tune our own performance to perform the way we want to do. People can always have a genetic advantage over their performance. It's why when you take two Olympians and they get together and they have a kid, that child will most likely have a genetic predisposition for athletic performance. So this next type that we're going to talk about is the fast oxidative. So you see the word oxidative in it, so you're still thinking with oxygen or aerobic. Fast has to do with the speed. These are intermediate fast twitch. So slow twitch, intermediate, and then we have fast. So intermediate fast twitch, they're a little more fatigue resistant and they're recruited second. The third is the fast glycolytic fibers, white. Okay, so all of a sudden we're going from oxygen loving or oxygen needing to not. Um, they're pale cells, they have a lot of filaments in them, and they have fast contractions. And again, that has to do with the enzyme working with ATP. It also has to do with the amount of sarcoplasmic reticulum around them. And these ones are recruited last, okay? So less myoglobin, poorer oxygen reserves. So the primary is the respiration of glycogen reserves, which we looked at before. Very strong and very fast. So let's compare fast glycolytic with slow oxidative. Slow postural muscle, now we're talking fast, really like a powerful hitting of the baseball, right? That's a very strong, fast contraction. In the middle with that intermediate, that would be like walking. There's some muscle contraction, but it's not a hard hit and powerful. So right. So slow, low intensity endurance activities, fast, medium intensity activities, and then fast glycolytic is short-term, intense, powerful. I'm just drawing your attention to this in the book. It comes right from your textbook, but this is a nice comparison chart of the 3 different fiber types. And here you see the recruitment order again, the rate of fatigue, which I think is important, right? Slow fatigue, intermediate, okay, it's gonna be in the middle, and fast. So it really breaks it down in a nice way, and it's definitely what we just talked about again, but it's organized in this fashion, which is nice, I think. Okay, so we're back to this article again. As you get further into a long run, slow twitch fibers that you've been using start to get tired. As a consequence, you start to recruit intermediate fibers, right, to help maintain the pace. And then you're going to get tired. So you might still be able to have one more powerful sprint, like at the end of the race, right, where you're tired, you've got nothing left, but you do this one last power where you use your fast glycolytic fibers at the very end, and then you're spent. You got nothing. Like they have to like carry you off of the finish line because you're done. So so let me show you where the rest of this article is. Right here, article on muscle fiber type. So if you click on that, I think it's a very nice, accessible article that talks about the types of muscle fibers, and they talk about 1, 2X, and 2A. And what I'll mention here, it might come up in the slideshow, but there's a little bit of interchangeability. You can train the 2A to become the 2X, or the 2X is more where you would go, 2X to become 2A. They can change their pathway a little bit. They're similar enough, but then they can be used differently. So the actual fiber type can change within the body during your lifetime. And then when you stop training it for fast power, it'll go back to its normal state. I've never heard of it going from type 2 to type 1, but between 2X and 2A, which is, again, so we have slow, intermediate, and then fast. Okay, right there. So I would recommend reading through this. It's different than reading a textbook, and it talks about a lot of things that we've been talking about. So I would encourage you to take a peek at that when you can. Now let's see if I can get back to where we were. Okay. Okay, so we have a swimmer and we have a jogger, and both of them can adapt their bodies to what they're going to be doing for their exercise. So adaptation to exercise. When we exercise, we change our bodies. The muscle capillaries increase, the number of mitochondria increase, and the amount of myoglobin synthesis increases, right? So if that's happening, that leads to a greater oxygen carrying capacity and therefore a better performance with aerobic exercise. It also will increase your strength and therefore, and with increased strength and increased in ability with aerobic exercise, you decrease the amount of fatigue or the onset of fatigue. Oh, and this is what I was saying for the two ones. Fast glycolytic fibers can convert into fast oxidative fibers. So, so if you do that, right, if you have fast oxidative fibers, then those are going to be allowing you to use the aerobic pathway to form a faster contraction. Typically anaerobic is weightlifting. Weightlifting, if I had to recommend anything, I would recommend walking every day, or at least walking like 40 minutes every other day, and then weightlifting every other day for 10 minutes. I would do weightlifting activities. But muscle hypertrophy, again, you get an increase in fiber size. There's also increase in your powerhouse, the mitochondria, number of myofilaments, glycogen stores, right? The more glycogen we have, the more we can draw upon for energy contraction. And then you also get an increase in connective tissue, giving you just overall power and strength and force. It does increase the muscle size as well. We're skipping this, anabolic steroid use. So testosterone plays a role during the puberty years in skeletal muscle development for males, typically, right? We're just going to talk typically here. And when you use synthesized testosterone, it will also lead to an increase in the ability to hypertrophy your muscles, and that has to do with protein synthesis. So it's not recommended to use these, but they are effective at doing what they do, which is hypertrophy muscles, as we see here. Side effects, though, there can be severe psychological side effects, including depression, as well as that roid rage, that like Jekyll and Hyde, where you're okay 1 minute and the next minute you're very ferocious or mean or something like this. You get a decrease in the genitalia, so the sex organs tend to decrease as well with males and with females. So you get like a decrease in breast enlargement, in breast size, but then you also get an increase in like the clitoris size. So there's a little bit of both here, but you kind of reverse your sex organs. And then here you can see there's a masculinization with a testosterone use. You get the effect of the muscle, but you also kind of have these other side effects, which may or may not be less desirable. Physically, we can say that it might not matter, like the physical appearance, but it's the internal organ damage that it can cause, and then the psychological damage that it can cause that is really the concern, and why it's advised to not use steroids. And then competitively, that's a whole other arena where people are competing athletically, and there's a call for no use of steroids. Kind of two different camps, but for overall health, you want to stay away from that kind of synthetic drug. Just a repeat slide on atrophy here, and some numbers. What's crazy is that as soon as you start weightlifting, right, you can build up your muscle mass so quickly. In 1 year, you can increase it, just so you can just get really strong really fast. I don't have a number for you. I apologize, but the moment you stop working out. So if I work out, I have been working out the same way every year or every week for years. So I weightlift 3 days a week and I walk and run 4 days a week, and then I go on vacation. And the minute I take a break, right, the day I stop weightlifting and I start laying around, my strength starts to decline as soon as you stop using it. So the more muscle mass you have and the stronger you are, a little bit of this decline isn't going to affect you too much. But nonetheless, as soon as you stop using it, it starts to happen. So this is So physical fitness is something that is an activity that has to be incorporated into your lifestyle, whether it's a habit or part of your career or part of your daily functioning, that you do things in a very specific way to maintain strength. You'll lose it. So we can really maintain our strength into our old age. You never lose the ability to keep your muscles from getting bigger and staying fit. Paralyzed muscles will atrophy and get very, very small. If they're paralyzed and there's no way for you to simulate muscle contraction, then you're going to end up with body mass shrinking. What also happens is it can be replaced with connective tissue. This is the one from Duchenne's muscular dystrophy, that childhood disease where there's connective tissue in place of where skeletal muscle was. So here the muscle size has decreased significantly. And in addition to that, the space, there's still some fill in that space. So you might look like you have muscle tone, but then when you go to activate it, you don't have the power behind it. Okay, so we rolled right through that, and I'm gonna wait for questions at the end so we can just get through the smooth muscle business. So a brief introduction. We spent this past couple of weeks looking at skeletal muscle, and what I want to point out with smooth muscle, there's a lot of differences, a lot of similarities. You can read through this section of your book to get the details of how muscle contraction works for small intestine or for smooth muscle, but I just want to give you like an overall picture. So an overall picture is that in general, these are flat sheets of muscular tissue that when they contract have like a circular motion contracting force, and that has to do with the fact that they're lining organs. All the organs except for the heart are lined with smooth muscle. So if it's a lining, when it's a contraction, it's going to lead into the squeezing. So the small intestine is a great example to use for this, because it's a little bit easier to picture that as food is moving through and nutrients are getting pulled out into the bloodstream, into the body system, there's a churning or a squeezing or a contraction. And we need that tube to be able to continue to squeeze the food matter through the intestines and all the way out for evacuation, right? It has to keep contracting to move that food through the system to get all the nutrients out and then remove all the waste. Yeah, I said this. Smaller single nucleus, a little bit about the structure. So there's no striations. We saw that in histology. There's a little bit of sarcoplasmic reticulum. The tone is there. They do fatigue without oxygen, so they're really oxygen dependent. And they're arranged in sheets of the walls of the hollow organs. So they are, they're also they have the greatest potential to become cancerous out of all the types of muscles. So we tend to find cancer in the organ areas, but including this in this area of the smooth muscle lining the organ as well. This is just a quick look. We have a neuromuscular, in skeletal muscle, we have a neuromuscular junction, and here we have these things called varicosities that send the impulse, and it leads to a large forceful contractile unit of the entire smooth muscle system. So it has a kind of, it's a slow input and then a slow response. It's sluggish compared to how a skeletal muscle receives a nervous impulse and contracts, and it's branched out in this way. So it's like a sprinkling as opposed to like a neuromuscular junction. On the skeletal muscle, you got the motor unit and it contracts in a hard way. Neurotransmitters are responsible for stimulating smooth muscle contraction. You have to have proper environment, so carbon dioxide, oxygen, and temperature. Hormones associated with the stimulation are oxytocin and gastrin. Hormonal levels change can initiate contraction of smooth muscle. So when women go into labor, for example, there's a change in oxytocin levels, and the change in that hormone will also stimulate uterine contractions when we're talking about that. So a hormonal level change initiates that contraction, and throughout the delivery process or the birthing process, it's that hormonal level change that allows the contraction to happen. There's also mechanically stretching that can lead to it. So this is why when you're in a yoga class, you go into spinal twist and they're like, oh yeah, wring out your liver, wring out your intestines if you're doing this reclined spinal twist exercise, because moving your body will compress the other muscles, will compress the organ tissue, the smooth muscle tissue. So the skeletal muscle tissue and the bones will compress the smooth muscle tissue, and that will lead to this muscle contraction. And when you're talking about like digestion and intestines, or and just the movement of fluid like in and out of the kidneys, in and out of the liver, that physical mechanical stretching that leads to contraction can be helpful in stimulating your system. When you have a well operating system, it's not that you necessarily need that in addition to how you're already functioning, but if things are a little kinky, maybe it can help to to twist a little bit and move some more to help your smooth muscle contraction. Injury normally results in repair with regeneration of lost muscle tissue. So the smooth muscle can undergo mitosis. And so therefore, if there's something amiss, it can regenerate and do well from there and continue in its normal functioning. Compared to cardiac, which gets replaced by the dense fibrous connective tissue, you can't, and skeletal muscle as well, it's less likely to be able to do. I think this is the last slide or so here. Just comparing the three muscle fibers. Again, if you go into your book and you look at these, at the end of chapter 9, there's a nice comparison chart where you can look at everything that we looked at in detail about the skeletal muscle fiber and then compare it to the smooth muscle and the cardiac. You'll look at cardiac again in the second section of this class 2. It's next semester, like 201. We're in 201, so it would be 202. So you'll get this in depth later. And a brief overview, I feel, is sufficient enough for smooth muscles. I hope you agree. So, and I said all that, and so that's the end of that. So let me stop the share. There we go. Okay. All right, so that's the run through. That's the gist of it. Do we have any questions regarding anything that went over in lecture right away that is important? No, you want to just take a look at maybe like a question and we'll call it a night?